Welcome to this session on ISO 26262 with model-based design, a hands-on Simulink tutorial with an X-by-wire example. In this session, we'll explore hazard analysis and risk assessment outlined in Part 3 of the concept phase, using a brake-by-wire system as our example throughout the discussion. In the previous session, we discussed item definition. The item definition gives the basis for HARA, as it describes the item's functionality, operational scenarios. HARA, in turn, can drive updates to the item definition. For example, a hazard analysis may reveal missing operational scenarios in the original definition. Together, they evolve until the system's scope, functionality, and safety requirements are consistently defined. To recap a few concepts in Session 1, a fault is the root cause of a malfunction within a system, such as a short circuit or a software bug. In a brake-by-wire system, a fault could be a transient voltage spike occurs in the power supply line due to load switching or inadequate power filtering. This electrical disturbance may affect the brake pedal position sensor, which is analog and sensitive to voltage fluctuations. This fault can lead to an error, defined as an unintended deviation in the system's internal state. In this case, the sensor might output a false signal, such as a pulse indicating 70% pedal depression, even though the brake pedal was not pressed at all. When an error propagates and causes the system violate its intended functionality, it results in a failure. Here, the brake-by-wire ECU misinterprets the faulty sensor signal as a real brake demand and activates the braking system. A hazard arises when such a failure has the potential to lead to a hazardous event, which could endanger human life or property. In this scenario, the brakes may be applied suddenly and forcefully while the vehicle is in motion, potentially locking the wheels. This could result in a loss of vehicle control, especially in high-speed or curved road conditions, creating a serious safety risk. A fault occurs at the component level. A failure manifests at the item level, and a hazard is observed at the system or vehicle level. System design and functional safety aims not only to deliver intended functionality, but also to ensure robustness against faults by detecting failures, mitigating their effects through safety mechanisms, and transitioning the system into a defined safe state when faults cannot be controlled, thereby reducing risk to an acceptable level. In addition, a hazardous event occurs when a hazard, under specific operating conditions, leads to a potentially unsafe situation in the operational environment that may result in harm. HARA evaluates hazardous events severity, how serious the potential harm could be. Exposure, how often the hazardous event might occur. And controllability, how easily the driver or system can prevent harm once the hazard occurs. To determine the Automotive Safety Integrity Level ASIL, which defines the required rigor of safety measures, and from this, derives the corresponding safety goals. HARA is a must in ISO 26262 as it provides a structured process to identify hazards, assess risks, determine ASIL, and define safety goals. It serves as the cornerstone of the functional safety lifecycle. Without HARA, safety-critical failures could be overlooked. We cannot claim compliance or prove the system is acceptably safe. And it's also relevant to development cost, since higher ASIL levels require more rigorous and more expensive processes and safety mechanisms. We will explore this topic later in the session. Hazard analysis and risk assessment methodologies draw on a range of complementary approaches to ensure comprehensive coverage of potential risks in safety-critical systems. Experience and legacy knowledge leverage lessons learned from past projects and known failure modes, while systematic analysis methods such as FMEA, FTA, and HAZOP provide structured ways to identify hazards. Simulation enables virtual testing of system behaviors under diverse scenarios, including rare and dangerous conditions, while human factors analysis focuses on operator interaction, usability, and error potential. Formal methods offer mathematically rigorous proofs of system properties, increasing confidence in correctness and expert judgment helps fill gaps where data or models are incomplete. Finally, field data and statistical analysis provide empirical evidence of failure rates and operational patterns, supporting risk quantification and validation of assumptions. Together, these methodologies form a robust HARA process by balancing qualitative insights with quantitative rigor. In this session, we'll show how simulation can be a powerful enabler for HARA, bringing hazards and risks to life in a safe, virtual environment. Here, we see the HARA workflow. We'll start by identifying potential hazard scenarios as the first step in the process. The first step is to define the operational situations, ranging from urban city driving to highway cruising, from uphill or downhill conditions to icy, slippery roads, and even unexpected emergencies. In Simulink, the Safety Analysis Manager helps us build a clear matrix of operational situations and directly link them to the relevant parts of our system models, creating a seamless bridge between scenarios and design. How does simulation help accomplish this? We start from modeling. Here is the top model in Simulink. It brings together the scenarios that define operational situations, driver models that follow predefined trajectories, the X-by-wire system, the vehicle dynamics, and the surrounding environment that provides road surface, frictions, etc., all in one integrated view. To dive deeper, looking into the scenario subsystem, it contains blocks that interface Simulink with Roadrunner, enabling co-simulation. These blocks exchange scenario data, for example, road geometry, actors, and trajectories, synchronize time steps, and pass control or sensor signals between the Simulink model and the Roadrunner scene to drive and evaluate scenarios. Roadrunner is a 3D authoring and simulation tool for driving environments. Use it to design road networks and terrain, add traffic infrastructure, and populate scenes with vehicles and pedestrians. It integrates with MATLAB and Simulink to enable closed-loop co-simulation for autonomous driving and vehicle dynamics and control applications. Within the vehicle subsystem, chassis and tire models capture road surface friction, grade, and elevation effects. The brakes subsystem integrates the braking systems and actuator controls, enabling realistic simulation of braking forces, stopping distance, and stability across varying terrain. The second step is to identify hazards, such as loss of function, incorrect function, wrong value, false positive or negative, out of range, unintended activation or deactivation, stuck on or off, spurious trigger, incorrect timing, response delay, jitter, out of sequence, and degraded performance. With Safety Analysis Manager, we can manage hazards and provides traceable links to relevant fault libraries. How does the model support this process? To examine the X-by-wire subsystem, which includes the brake-by-wire control design, we conduct fault injections within the brake control subsystem targeting the right front and right rear brake pressure signals. Furthermore, in Simulink, the fault table provides a structured way to define and manage fault injections. It supports various fault types, such as loss of function, complete or partial signal or component failure, unintended command, unexpected activations, noise, random perturbations, gain, incorrect scaling, and offset, fixed bias. The table lets you specify the affected components, fault timing, duration, and magnitude, and easily configure single or multiple concurrent faults. By centralizing fault definitions and managing their injection, the fault table enables repeatable simulations, facilitates tracing how faults propagate through the system, and helps identify potential safety or performance impacts. We have now walked through identifying hazard scenarios, including defining operational situations and identifying hazards. Next, let's move on to assessing risks and determining ASIL. There are three key factors that are considered: severity, exposure, and controllability. Severity measures the potential consequences of a hazard if it occurs, such as the risk of injury or damage. Higher severity indicates more serious outcomes. Exposure represents how frequently the operational situation that could lead to the hazard occurs. A hazard that is encountered more often has higher exposure. Controllability evaluates how easily the driver or system can prevent or mitigate the hazardous outcome. If a hazard is difficult or impossible to control, controllability is considered low. By assessing severity, exposure, and controllability for a given hazard, we can determine the corresponding ASIL using the ASIL determination table, which maps these factors to the appropriate safety level. How can simulation help in assessing risks? Let's take a look at some demonstrations. In this demonstration, a vehicle is traveling on a flat road at 50 kilometers per hour, with the brake pedal applied to 60%. On the left, we will show the vehicle's normal braking behavior, while on the right, we will illustrate a brake failure scenario, where both the right front and right rear brakes experience a 100% loss. Let's begin the simulation. Next, the vehicle speed is increased to 100 kilometers per hour. To continue, the vehicle speed is increased further to 150 kilometers per hour, and then to 200 kilometers per hour. To move on, we evaluate brake loss failures under low friction conditions on an icy road. Next, the vehicle speed is increased to 100 kilometers per hour. To continue, we assess brake loss failures while the vehicle is on a downhill slope. Next, the vehicle speed is increased to 100 kilometers per hour. Last but not least, the brake pedal is fully applied, and we compare vehicle behaviors on a flat road versus a downhill slope at 150 kilometers per hour. All right, by leveraging simulations, we can analyze the severity, exposure, and controllability of hazards and assign the correct ASIL. Once again, the Safety Analysis Manager helps manage this process and provide traceable links to the models. We have now walked through assessing risks and determining ASIL. Next, let's move on to defining safety goals. In the HARA process defined by ISO 26262, safety goals are derived as the top-level safety requirements. Once hazards are identified and their risk levels are assessed, considering severity, exposure, and controllability, The outcome is translated into high-level safety goals that describe how the system must behave to avoid or mitigate unacceptable risks. These safety goals serve as the foundation for all subsequent safety requirements, guiding the functional and technical safety concepts and ensuring that the system design remains aligned with safety from the very beginning. Now we have completed our walkthrough of the HARA workflow. Here are examples of risk assessment and ASIL assignment for a brake-by-wire system. Feel free to pause here and read through them. Here are examples of safety goals derived from the previous case. Again, feel free to pause here and walk through them. In the previous session, we noted that higher ASIL levels demand more rigorous and often more costly processes and safety mechanisms. In this session, we'll take a closer look at what that means in practice. The cost drivers across ASIL levels in ISO 26262 primarily stem from the increasing rigor required as risk criticality rises. At lower ASILs, costs are relatively modest, focusing on basic process compliance and documentation. As ASIL levels increase, costs rise due to more stringent development processes, for example, stricter coding guidelines, traceability, and tool qualification. Verification and validation activities, such as extended testing, fault injection, and coverage analysis, and the addition of safety mechanisms, redundancy, monitoring, diagnostics. Higher ASILs also require more comprehensive configuration and change management, independent reviews, and often more qualified personnel and tools, which further drive up expenses. Ultimately, the jump in cost from ASIL to D reflects the greater assurance needed to mitigate hazards in systems where failures could lead to severe or life-threatening outcomes. In a brake-by-wire system, a hazard such as brake force deviating moderately from the driver's input might be classified as ASIL-B, since while it can reduce braking performance, the driver may still maintain some control and mitigate the situation. The safety requirements here would focus on implementing diagnostics, plausibility checks, and controlled fallback modes. On the other hand, a hazard like complete loss of braking at highway speed would be rated ASIL-D, as it poses an immediate life-threatening risk with little to no chance of driver controllability. This highest classification demands rigorous measures such as redundant braking paths, fail operational architectures, real-time monitoring, and exhaustive verification and validation processes. The contrast illustrates how the severity and controllability of hazards directly influence ASIL assignment and the resulting safety mechanisms. HARA is inherently an interdisciplinary effort, requiring expertise across domains such as creating scenarios, vehicle dynamics and control, system and architecture design, embedded software and hardware, functional safety, and human factors. To effectively bring these perspectives together, tools like MATLAB and Simulink provide a unified environment where scenarios can be defined and simulated. Vehicle dynamics and control strategies can be modeled. System and architecture designs can be evaluated, and safety workflows can be seamlessly integrated. This holistic approach not only supports collaboration across teams, but also ensures that safety considerations are validated in context, bridging the gap between theory, design, and real-world operation. A powerful toolchain supports end-to-end safety analysis and design by combining specialized tools within a unified workflow. Roadrunner enables the creation of rich scenes and driving scenarios, which can then be simulated in Simulink as the central simulation platform. The X-by-wire control systems are designed and tested directly in Simulink, while the physical vehicle dynamics are modeled with Simscape for realistic behavior. To evaluate robustness, Simulink Fault Analyzer allows systematic fault injection and analysis of failure effects. Finally, Simulink Test provides automation for running, managing, and analyzing large sets of safety-related experiments. Together, these tools not only integrate environment, control, hardware/software design, and fault analysis into a seamless workflow, but also help conduct HARA with model-based safety analysis, ensuring hazards and risks are assessed within realistic system contexts. All right, let's wrap up. In this session, we covered why HARA is essential, explored the full HARA workflow, and demonstrated how simulations can support hazard identification, risk assessment, and safety goal derivation. I hope this session has given you a clear understanding of how model-based safety analysis can bring together scenarios, system models, control design, and verification to create safer, more reliable systems. In the next session, we'll explore the functional safety concept from Part 3, the concept phase of ISO 26262. I look forward to your participation.